In this section, I will explain about the junction capacitance and the Schottky diode. In the PN junction diode, there is the region where the mobility carrier is depleted, and this is called the depletion region. In this sentence, we can deduce that there is some characteristics like the capacitor, so we can find the capacitance of this capacitor. But how can we uh, find this capacitance? As we know, the formula of the capacitance C is equal to the permittivity epsilon multiplied by uh, area A and divided to the length D. And here A means the cross-section area of the diode, and here D is equivalent to the width of the depletion region. And as we know that the formula of the depletion region, the width of the depletion region is square root 2 multiplied by epsilon multiplied by junction potential Vj and multiplied by the sum of the donor concentration and the acceptor concentration and divided to the charge quantity Q and multiplication of each concentration. So the capacitance C can be reorganized like this formula. And also, we can express the junction capacitance same as the diffusion capacitance, because this junction here in junction, the depletion region is can be exist can exist by the diffusion of the by the difference of the carrier concentration. And as we find the capacitance C, and we can derive the some differential equation, a differential relation, which is capacitance C is derivation of Q by the voltage, applied voltage, because yes, and then this Q can be expressed to the yes, this dq means that the some lifetime tau n and multiply to the differentiation of the current. So yes, diffusion current. So this is the example of the p-type semiconductor. And so this formula EQ divided to dA, dQ dVA can be reorganized like this: tau n multiplied by d a differentiation of the diffusion current to the differentiation of the voltage, applied voltage. And here this derivation formula is the reverse form of the resistance, and this is called the conductance, and this can be initialized to the G. So the capacitance C can be re-expressed to the tau n and multiplied by conductance G. And there is some another structure of the diode. In this PN junction diode, this characteristics is the junction of the two semiconductors, but this Schottky diode is the junction of the metal and the semiconductor. Well, how can this act like a diode? As we know that when the two semiconductors meet each other, the Quasi-Fermi level of each type of semiconductor is moved, make a thermal equilibrium, and this metal and semiconductor structure can act like to satisfy the thermal equilibrium. So the quasi-Fermi level of the semiconductor can be moved to make the same level to the metals, Fermi level of the metal sorry, I will say it again. To make the same level to the quasi-Fermi level of the metal. So this band structure of the semiconductor is swerved like this, and to swerve like this and make the built-in potential as the difference of the quantity of the curving. And here the originated level of the conduction band to the quasi-Fermi level of the metal is called the Schottky barrier, and this is the indicator of the conductance of the diode. This is the examples of the metal and the n-type semiconductor, and universally there is also the metal and junction of the metal and the p-type semiconductor, and which can deduce that the Fermi level of the metal is higher than the Fermi level of the p-type semiconductor. So to make the thermal equilibrium, this Fermi level of the p-type semiconductor moves up to make the same level of the Fermi level of metal. So the relation is converse as the metal and n-type semiconductor junction. So here, the Schottky barrier can be expressed like the difference to the metal quasi-Fermi level of the metal to the quasi-Fermi level originated the valence band level, and here the curved quantity of the band means the built-in potential. Thank you.